Okay, I think we can now actually start officially, and it is recording. Gotta hate those updates, but looks like we're back. Welcome back, everyone. For the announcements today, I just want to remind everyone that this was pointed out just a few moments ago, that assignment number 7, its official due date is pushed back to Monday, October 16th. If you haven't done it, you want to turn it in either today or on Thursday's class, the usual due date, that'll be completely fine. But that's only because of our second exam. So we completed our second exam. The solutions are posted here. And did I forget to pass it back to anyone in class at the moment? Okay, if you're in Zoom, you're just not here today, then you're also welcome to get your exam back scanned. Just send me an email and I'll be very happy to do that. Oh, let me pass one back. So on this exam, if you're curious about some of the summary statistics, average came out at 78.1%, and there was a two-way tie with essentially 97% altogether. So excellent work on that exam, folks. Well, any questions that folks have about the second exam that you would all like to talk about or otherwise? Yeah, go ahead.
What was the average?
The average came out to 78.1%. Comparing that against exam 1, let's take a look at that. Exam 1 had an average of 83.1%, so we're about 5% difference on that, with 100% as a two-way tie. We had another two-way tie. I can't say if it was the same people or not, since we have to keep that information private. It is private information, but 96.9% with a two-way tie on this one. Other questions so far? Okay, maybe just to mention one of the problems on this exam, let's open up the solutions right here. The most challenging problems I would say were, if I scroll past it, there it goes. I would say problem number 5 was the trickiest one. Essentially what was happening with problem number 5 is we had to know what's a constant and what's not a constant. So say, for example, this one right here, because it does involve x, this one is an exponential function, a bona fide one. And if you differentiate it, you get the exponential back and the logarithm multiplying with to the same base. But this one right here, here's the kind of trick to it. It's indicated as a g of x function, but there is no x apparent here whatsoever. That means it must be a constant. In fact, you could calculate this and see what it comes out as. And the derivative has to be 0 for anything that is constant. Even if there was a variable, but the variable wasn't x, we put like a r there or an a or something weird like that, maybe a k, it's still constant if the function is indicated as g of x. X forces it to be the independent variable. So differentiate that whole thing and you get a 0. Similarly with h of x here, that's just essentially 2.7 to the power of 8, another constant. So it must be 0. But finally right here, if there's an x apparent, that's the variable of the problem. And x just goes down below with the log, natural log of the same base of that logarithm. So to me, that looked like it was the trickiest question on the entire exam, really. Because once again, it was about what's constant and what actually varies. Any questions at all, folks, about problem 5 or others?
How would you do that?
The A right here,
Yeah.
it's really pretty much based off this formula. Once I get this tool to work. Sorry, once again, they updated my stuff, so it's all kind of weird. But the formula goes d by dx of a to the x is always a to the x, so itself, times natural log of a. So that was our formula that was working under the hood for that problem there. Other questions so far? Okay, well, the current section we're in is section 3.10. We have 2 more loose topics to take care of before we go off to chapter 4. And so next week we'll be officially in chapter number 4. Chapter 4 is about applications to the derivative. Some of them are related mathematical theorems, but other ones are actual real applications to the real world. We'll be looking at optimization as one of our major highlights. But first, let's get back to our current notes so we can get to that location. So we're back to section 3.10 on linearization. And for this current topic, it really looks like we're getting to something nasty if you read through all this. But before we trudge through the definition, here's a great way to think about what's really happening if you're talking about linear approximation or linearization. You'll always have a function that's applied. So there's going to be a function y equals f of x. Now suppose we want to linearize this, or instead of saying linearize, let's say find the tangent line equation at, let's call this x equals a. So if we did that, well, first thing we have to do is come up with an entire point. X being a is not good enough. We need an x coordinate and a y coordinate. So next thing we would say is, if it's going to be at x equals a, it'll go through a, f of a is the point, the tangent line goes through. So if they give us a function, y equals f of x, we'll have several functions to look at in these notes. Supply us with an x coordinate, and we can come up with a point. Only thing we need to get the actual equation for the tangent line is a slope now. That's the last missing ingredient. But the slope goes like this. The slope m, let me put it in a location where we can fit things. The slope m is the derivative of f at a. So we take that a coordinate right there, plug it inside the derivative, and that's going to be the slope of the tangent line at any valid a value that's in the domain of the function. Next thing we would do is take any equation that can build the tangent line. In this course, I usually use this. Some folks have gone a different route, which is completely fine. So you're fine to stick with, say, the slope-intercept equation. But we went y minus y1 equals a slope m times x minus x1. So we can plug information right here and get our tangent line back. The y1 in this problem is just this right here, the f of a. The x1 is this right here, the a itself. And the slope, I used a different color. The slope m is just the derivative of f at a. So putting this all together, we can say that y equals a y1. That's an odd place to put y1, honestly, it really is, but it works. Plus m times x minus x1. So I have a y1 here I want to track, and x1 here we'd like to track. And this is pretty much the steps of building a tangent line equation. We did this in chapter 2. We did it several times in chapter 3 as well. And we'll be doing it a lot in these notes here. Any questions with our sketch down below? Okay, so now if we look at linear approximations, it feels like it's an entirely different concept, but it's really the same idea. Let's look through this to see what they're saying here. We'll use the tangent line to a function f at a point a f of a. That's where we're dealing with. As an approximation to the curve y equals f of x, when x is near a. The equation of the tangent line is given in this format, y equals f of a plus f prime of a times x minus a. And this is the approximation by that linear function, the tangent line. We'll call this function, the one on the right here, the linearization to f at a, or the tangent line approximation. It comes written into this format right here. So when we say linearization of f at a, we're talking about that function L of x. Let me try harder with the arrow. But take a look at that L of x. That is the tangent line equation, really. I feel like when you break into these notes, that's always the first thing you want to think about, or else the notes feel way more abstract than they really are. So comparing them, our y right here is the L of x. The f of a right in this location is the f of a right here coming from the y1. Then we have a slope f prime at a. Down over here, we just wrote it as M, but you could just indicate it as f prime at A, and that's just fine. And then we took x minus A right here. So that's a linearization of f at A. So really you have to do two things to find this. You need, well, three things. The first thing is you calculate f of A. That's an ordinary function computation. Second thing, calculate the derivative and evaluate it at A. And the third thing is just put it all together and you've done the linearization, which is the same exact thing as finding the tangent line equation. So we'll be looking at this a little bit more today. And differentials, this will be a really short topic for us. The differentials will come into play in chapter 4, or integration. So it's kind of an odd choice. Our author introduces differentials right here and now. That's not a bad thing to do. And there's a lot of work that you can do to show a differential is just another way to think about a linearization. But the real reason we care about differentials and the real thing we'll do with them is all the way in chapter 5 when we're doing integration. So kind of a weird topic that we'll pause for a moment and come back to in a few weeks. Any questions, folks, before we try out one of these linearizations here? Okay, let's give this a try. And I forgot I have some special problems I want to put down on the notes here. So let me remind myself what those are. And here's what the work is going to look like. It says, find the linearization L of x of a function at A. Let's call this one part A. The function f of x is going to be given as x cubed minus 2x plus 3. At, let's do this one at A equals 2. So that's the computation we'd like to do here. Essentially, people say linearize the function f. Why would you ever want to do that? Well, if you're doing some complicated situation, maybe solving multiple equations, dealing with differential equations, sometimes these functions just don't play nice, and you can't get an exact solution no matter what you try. But if you linearize your function, you can at least get a very robust approximation to whatever those equations might be. So this is an application of itself, but the real applications would be like in an applied setting, in a physics class or a chemistry class and so on, possibly engineering for sure. So to try this out, well, first thing we have to do is just differentiate the function, or let's actually evaluate the function at A to start. When it gives us the A equals 2, we should calculate f of A immediately. F of A becomes f of 2. So we're just plugging in 2 for x to get 2 cubed minus twice 2 plus 3. So this is something like 8 minus 4 plus 3. Looks like a value of 7 altogether. That's pretty much always going to be my step 1, where I linearize, just evaluate the function at A. Because it gave us an x coordinate, and this is the y coordinate. That's the reason to do all that. Next thing we'll want to do is differentiate this. Let's call this f prime at x. The derivative of f at x is going to come out as 3x squared minus 2. So nothing too major. And now for the next step, take and evaluate f prime at that A equals 2 once again. So the derivative of f at 2 becomes 3 times 2 squared minus 2. That's going to be 12 minus 2. For a value of 10. So we have two interesting ingredients. We have an output here, so that's a y coordinate. We have a derivative evaluated at 2, so that's truly a slope. Next thing we do is write down the linearization formula and substitute in the information. So the linearization of that function f of x is always going to be given as an f of A plus f prime at A times x minus A. That value A is really what's dictating everything. That's the x coordinate that they supplied us. Plugging it all in, we get linearization at x equals f of a is this value way over here at 7, plus down over here where it says f prime at a, I wanted to put maybe a little bit additional here just to show the substitution better. F prime at a is the f prime of 2, but it comes out to a value of 10. So 10 goes in, and we multiply that by x minus the a value again, which is 2. So drop in your 2, and you've got it, folks. That's the linearization of that function. If you want, you could simplify this a little bit further, but sometimes people actually leave it in this format. As wild as that seems, our algebraic training says always try to expand things and simplify by combining like terms. But if you left it in this form, here's what it reveals. It reveals that that's the second coordinate, and that that's the first coordinate where the linearization occurred. Well, we'll always know that that's the slope, whether you expanded it or not, because it's multiplying x. But some folks leave it right in this format just to show all those pertinent pieces of information. But if you want to expand it out, that's completely fine as well. You could get L of x equals 7 plus 10x minus 20. So the linearization of x, I'll write it as 10x minus 13. So we did it, folks. Really what this was is a glorified tangent line equation problem. It just happened to have a new way to present the information as that L of x function there. Any questions at all getting through this one? Okay, the good news about this kind of process is there's always a really fast check, as a homework problem at least. If you're doing this as homework, never a bad idea to just have any graphing software ready to go. Because a lot of your checks are just purely visual. So to check out this right here, let's go to the graphing calculator, place in the original function f of x. It's x cubed minus 2x plus 3. Throw in the linearization, L of x equals 10x minus 13. Let's just see if that looks like a true tangent line equation. So right at x equals 2, we get the value of 7. So that's where the linearization happened. And that looks pretty accurate. If you wanted really, really good information, just zoom in on this 0.27, and you should see that eventually both lines are overlapping completely. That means the original cubic polynomial is exceedingly well approximated by 10x minus 13, as long as you stay very nearby 2 for your x coordinates. If you do that, then you're in really great shape. Any questions at all, folks, on getting through this problem? Okay, so that's linearization in a nutshell. Let's try it out for a part B. So this time, let's linearize kind of a wild function. This one is going to be, let's see here, f of x equals tangent of x. So now we have a bizarre trigonometric function that we're working with. If you're going to work with this, maybe solving equations, things like that, equation solving is not too bad as long as they give you a right coordinate. Like you could solve tangent x equals 0. That would happen at 0, pi, and so on. But if you're solving a more complicated equation, you need a good approximation. Linearization might be a good way to go on this one, because tangent is a complicated function. Say you're wanting to solve an equation nearby where something happens around pi. That means we should linearize around pi. So we'll be at a equals pi. A little line here just to say brand new problem. And really same exact kind of approach. First thing we'll do is calculate f at a. The a value is supplied pi right here. So f of a then turns into tangent of a. Which will come out as tangent pi. Next, well, tangent pi is sine of pi. Divide by cosine pi. Sine of pi is 0, so we're getting a value out as long as the denominator is not 0. And we're okay. Cosine of pi is -1. So the value becomes 0 altogether. So that's our first step. Next thing we do is we have to differentiate the tangent function. Any volunteers for the derivative of tangent? Good call. We get a secant squared right away on that one. So f prime at x is secant squared x. We need that as an intermediate step because what we really want is f prime at a, which will be f prime at that value pi indicated. Then go to your derivative, f prime. We're just throwing pi inside secant squared. So this becomes secant squared at pi. Well, this one's really fast to calculate. Secant squared, well, secant itself is 1 over cosine. So secant squared is 1 over cosine squared. Evaluate at pi. Cosine pi is still -1. So all we're doing is squaring -1. This becomes a value of +1. And now we're just throwing in our values into these 3 different positions. And our work is complete. Does that look right, however, to this stage, folks? Awesome. So now finally, we can say the linearization L of x is going to be, first grab our f of a, that came out as a 0, plus, next is going to be f prime at a. I'm really looking up here where the highlighting is in yellow. F prime at a, we come down and just grab the value, it's a 1, multiplying back up to the formula, x minus a, so it'll be at x minus pi. Then this one simplifies pretty quick. The linearization is now equal to just an x minus pi altogether. Well, we did it twice now. That's our second linearization. We'll do a few more before we're done with the notes today. But any questions or comments, folks, on getting that x minus pi? Okay, well, again, the punchline of why you want to do this is always really, really important. It's helpful in example 2 as well. So let's mention it right here, just in the comment pen. The only reason you would ever want to linearize like this is because you're interested in certain values of the original function around pi. We can now say something to this effect, that tangent x is now approximately x minus pi whenever x is near pi itself. So if we take values, say like 3.2, 3.05, we'll probably get really excellent approximations through here. In fact, let's test it out just to see how good it does. Here, I just want to use the calculator tool this time and just focus on the numeric portion. Let's suppose you want to calculate, say, tangent. Not at pi, we know that value, it's 0. Let's suppose you needed to get a good approximation of tangent 3.17. I mean, the calculator does it, there's that approximation. Or if you're solving an involved equation that uses tangent in several steps, you probably need to use a linearization if you need an approximate answer. So if we put 3.17 for x minus pi, compare the digits, that's a really good approximation. In fact, I think I need a tool to see where they differ. So 0.02841, 0.02840, that's the first place they differ, and not by much. In fact, if we rounded to that place, they would be accurate to 1, 2, 3, 4, 5 decimal places after rounding. That's kind of amazing, which is kind of a basic linearization. We do really pretty good at calculating tangent 3.17. That's only because 3.17 is pretty close to pi. Put in something that's far away from pi, and this will break down really badly. Let's try that out, and then we'll try out the next problem. Oh, I want to clear all drawings. There we go. When they updated this, they didn't change anything. They just looked different. So now I'm kind of relearning where all the icons are. So now suppose you want to calculate tangent at 64. That's not too bad. There's our value, 2.347. If we try to use the linearization, we'd be putting 64 here minus pi. 64 minus pi. Now we are super off on our computation. It didn't work at all. That's because we're using a linearization that only gives accuracy if you're close to about 3.141. At 64, all bets are off. It's really a pot shot if we'll be close to the right value or far away from it. Well, let's try out the next problem then. First, any questions or comments about linearizations or tangent lines, which are essentially the same? Okay, so our next problem is really based off a problem that was on the homework as well. It's a great problem that is discussing this. It's in orange right here. But the tough thing about this problem is there's really like 4 parts hidden inside this one little statement. So let's take a peek at the homework assignment for just a moment. I want to show you which one we're taking a look at. It's going to be that problem number 6 in section 3.10. That one's worth 20 points because it feels like 20 points worth of work. There's really multiple parts there. So this is homework 6. I'm not saying it's exactly homework 6, but this is a good place to go if you're worried about getting through that problem there. It says, find the linear approximation of the function g of x equals natural log 1 minus x at a equals 0. Use it to approximate 2 things, a natural log 1.5, natural log 0.99, and then illustrate by graphing the tangent line equation and the graph of g. So lots of things to do. Let's start just right here. Let's linearize first and make that our first portion. I'll call this 1 for the first thing we're going to do, or you could call it part A for the first thing. We have g of x equals the natural log of 1 minus x at equals 0. So that's the base point where the linearization happens. First thing to calculate, I'm just going to make sure the color coding is the same. Okay, we'll do this in blue. First thing to calculate will be g at a. That gives us g at 0. So over here, this will turn into the natural log 1 minus 0, becoming the natural log of 1. And then the natural log of 1 back to 0. Lots of zeros on this one. So our first term comes out to 0 on this. Next thing we need to do is differentiate g of x. You know, that derivative is actually kind of tricky. This one involves the chain rule because we don't have just x inside here. We have 1 minus x. So let's go for g prime of x. First thing we differentiate is the natural log function. It'll go like this, 1 over some quantity. But then by chain rule, we'll multiply by the derivative of whatever that quantity is. The 1 minus x goes into both of those locations, so it'll come down right here and right here. So now the denominator of the first factor is done. We don't need to worry about that at all. We'll just call it 1 minus x. Anyone see what should be thrown into the numerator? Exactly. The 1 here goes to 0. Derivative of negative x is negative 1. So we now have our derivative, kind of a tricky one to get through because of sometimes it's just not easy to spot a chain rule if it's not a built-up function like x squared plus 5x. But now we're ready for our next portion. We need the derivative of g at a. A is 0, so we're calculating g prime at 0. We already calculated g prime at x, so in all this work, 0 goes into that location. So it's negative 1 over 1 minus 0. That just resolves to a negative 1 altogether. So finally, we're about ready to put down the linearization. First, it's always a good idea if you're learning a new formula. I mean, it's still a tangent line, but it's in a new format as a formula. Always a good idea to write it down first so that we can slowly start absorbing it. Linearization at x is going to be equal to, first, it's the function evaluation g of a. Then we'll add to that the derivative of g at a, so g prime at a, and multiply that with an x minus a. So in our process, really we have all the values that we would need. G prime at a is going to go to a 0. A here turns into a 0, and g prime at a turns into a negative 1. So altogether, linearization at x is now equal to 0 for this location plus a negative 1 for g prime at a, multiplying x minus 0 altogether. That's a lot of substitutions. And honestly, I think that's what's tricky about the linearization, whether you're doing it as an L of X function or as a standard tangent line problem. There's a lot of values to keep track of and a lot of substitutions that happen in that process. But at the end of the day, we have that the linearization at X becomes negative X, and now we're in business. This is a long problem though, so I would definitely suggest doing the following if you're doing this as a homework problem. I would skip to that part right there, because if my graphs don't even look right, why worry about all this other work and the approximations? That would be effort that has to be undone if we made a mistake. So let's take a look at this inside Desmos. Let's give it the original function, g of x to start. G of x equals natural log 1 minus x. And it's on there somewhere. We'll try to get it back if I can't get it quickly. And there's an axis, so we're in good shape. And there's our function. Next, for L of x, this is going to be negative x. And I would agree with that picture there. That looks about right. So when it says illustrate by graphing G in the tangent line, you really have options for that kind of problem. If you're working digitally, you can just take a screenshot of this and put it in your notes. You would essentially go with a snipping tool. And I would be happy with that. That's always completely fine. Or if you're working the traditional way, paper and pencil, paper and pen, like a lot of folks are, here's another option you could take. I would still look at a graphing utility and just put down something along these lines. Doesn't have to be an excellent graph. I don't need a lot of values. We're just trying to illustrate which is the function, which is the tangent line. So I'd probably go about like this. Let's label this as g of x. And I think our g of x has kind of a different feature. We're not trying to do it perfectly, but that's a vertical asymptote right there. So I'll try to draw it a little bit more in that way. So we have a g of x function here. And the new thing that we're very interested in is a linearization, negative x. They'll intercept at the same point and look about, oh man, I said we didn't want to go too nuts here. Let me try, oh geez, let me try drawing the line first. I think that might be a little bit easier. Negative x goes like this. And now redo on the g of x function. I definitely graphed it weird. I had an intercept way up here. It crosses through the origin, matching up with negative x right here. So next try should look about like this. So that's the g of x. And this one is the linearization, L of x. Definitely kind of a slog on that one. But again, I didn't put any values here on the axis, either x or y. We just want a qualitative look at it. Let's leave that one as our official response to illustrate by graphing G in the tangent line. So there's G in black and the tangent line in purple right there. Well, any questions so far, folks, to this stage? Okay, we still have a couple things we've got to do. We need to approximate natural log 1.5 and natural log 0.99. Let me put it down here so you know what we're doing without having to scroll repeatedly. But this was the first thing we had to do. I would call that 5 points to just come up with the linearization. This is the second thing we had to do, come up with the graphs. That'd be the second set of 5 points. And here's the third thing we'll do. First, I'll approximate natural log 1.05, and then we'll approximate natural log 0.99 for the fourth thing altogether. Before we go and do that approximation, let's put in a reminder about all of this stuff. We kind of see it on the graph, and that's why our author wants us to do the graph. G of x is essentially exactly L of x. Well, it's exactly at 1 point, but everywhere else, it's extremely close. As long as you stay nearby a value of 0. If x is near 0, you have an exceedingly excellent approximation to the logarithm with negative x. Doesn't get any nicer than that. So let me write out this way. The natural log, let's put this in black actually, because it's definitely an essential part of getting through this. the natural log of 1 minus x is approximately equal to negative x for x near 0. We're seeing it on the graph, and now we're going to see it numerically as we approximate natural log 1.05. Any questions, folks, before we start? Okay, at the moment, this doesn't look good because we want to approximate for x near 0. 1.05 looks like it's far off, but that's not the quite right way to think about this. This problem is a little bit trickier than it seems. So let's go through this next phase really, really slowly. I'm going to start at natural log 1.05. But our goal is to make it look like this. Natural log of 1 minus, so that we can reveal what is the actual value of x in this problem. That's what's tricky to find, that x right there. If we could spot it, we'll use our approximation, throw that same x right here at negated. So let's give this a try. It starts as natural log 1.05, but we have to match the format of the original function g by that red dot. So we'll go natural log 1 minus to carry that format. And now we just need to place a value in right here so that when we crank it out, we get 1.05. Anyone see the number that must go into that location here? Negative 0.05 would do it, absolutely. If you put a negative 0.05, let me try and make this actually fit first. Put in negative 0.05, then 1 plus 0.05 is what this turns into, getting us back to the 1.05, which we originally started with. What do we do here? We reveal the actual x value that's going inside this x, giving us the approximation through the linearization L of x, and then we'll just switch the sign. That's our approximation right there. And we should expect accuracy because negative 0.05 is sort of near 0. It shouldn't be terrible. So let's see what happens on the next step. Here's the approximation. It becomes negative, or whatever you said x was, negative 0.05 right here. I would say that in this problem, the color coding is really, really essential. Watch the yellow and the purple here for color coding. Yellow is trying to get the function in the right format, so we could go across this approximation. But when we go across the approximation, we're carrying in that number right there. So this turns into 0.05. I'll put a box on this one because it's kind of conflicting with the graph right over there. But one thing that's kind of weird about all this is, well, how would we check this? I would check it by just grabbing a real calculator and not doing an approximation. So kind of a strange problem. Let's see how close we got to all of this. We have a 0.05 we're comparing with, and the thing that we're approximating is natural log 1.05. The calculator says this should be about 0.0487 and some change. If we rounded it to decimal places, they would agree, but we're only agreeing to 2 decimal places of accuracy after rounding. That's not really terrific, but we weren't super close to 0 either, so we should be forgiving on that. That's an okay approximation. One thing you might wonder is, what did the calculator do though? The calculator is more accurate. What the calculator has really done is they've taken this L of x function, which involves a power of 1 right here, and they added a quadratic term. The linearization can extend to more terms. Then the calculator might have added a cubic term, a 4th power term, and so on. Essentially, they're putting a Maclaurin series or a power series right here and calculating it out in that way, giving us a decent enough approximation. That's the kind of stuff you'll get into in Calculus 2. Here, we're just looking at the very first term. In fact, let's take a look at that just to see how does that even tie in. Let's take a look at, we want power series. Images might be okay. And a power series take a look at one that looks a little bit better. Images are sometimes kind of rough. This is a little bit better. Power series essentially look like this, where you have multiple terms all trying to approximate the same exact thing. We are really only putting in the very first approximation when we stopped right at this stage right here. So that's the constant term, that's the power one term, and more terms can keep on being added onto this to give us even more accuracy until eventually you have a power series representation of that entire function. So that's kind of interesting stuff. But let's try this out again by doing natural log 0.99. Any questions at all first, folks, about the approximation here? Okay, so this is the fourth and final part. We're nearly through it, folks. We want to approximate natural log 0.99. I think we can delete this screenshot then. Well, that's a copy paste. For natural log 0.99, we need to do the same approach. It's all about what's happening way up here, where we wrote that approximation through the linearization. We'll start off as before and write natural log 1 minus. Because we have to match up that format of the original given function g. Then something has to go right here for us to get the 0.99. Anyone spot what the value would be in that location? Exactly, 0.01 will do the job. I think this one's friendlier because here we had to do double negation to make it work out. But here subtraction does the job. That's the critical x value we need. And notice the 0.01, much closer to 0 this time. So we should expect much higher accuracy, more than 2 decimal places of accuracy at this location. But right now we're at this portion, circled in orange right here by the red dot. Once you have spotted your x, just invoke the linearization step. We'll say that that's approximately equal to negative sign because that was part of our linearization, and whatever x turned out to be. So 0.01 would go right exactly here. So it should be negative 0.01 for our approximated value. And it should be negative. Natural logs become negative if you have a value less than 1. Now checking Desmos just for how accurate this one came out as. Take natural log 0.99. And this is negative 0.01005. The difference is in the 5th decimal place. So we really do have 4 decimal places of accuracy if we put in those additional zeros, which is valid, but just weird looking. So we did it, folks. That's the linearization and the additional questions of doing approximations with it. The approximations are kind of silly for the moment, since there's nothing major happening. I mean, if society collapses and we can't reach for a calculator, can still approximate that. But its real value is more about that picture, understanding the concept that the tangent line equation, the linearization itself, is the best local linear approximation of g of x near 0. We see it through the graph, and we see it through actually approximating it to test it out. So I think that's a big takeaway on these 2 portions right here. Well, any questions at all, folks, before we change gears a little bit? Okay, so linearizations are its own thing. It's not too bad to get the L of x, but these questions are always tricky if you have a further approximation. Yeah, question?
So the answer to that one is
Exactly, yeah. So that would be our answer on here. And positive 0.05 on the 3rd part right here. Other questions so far? Yeah.
so where was like the LM 0.99? Where would that be?
Oh, the 0.99?
Yeah, it is one.
We would be somewhere, let's see, if this is our value of 1, we'd be somewhere around here in particular. The trouble with our graph is this g of x is not the standard natural log. What was plotted was that function there, which caused a reflection and a shift as well. Does that make sense though so far?
Oh, yeah.
Yep, you betcha. Other questions so far? Okay, well, let's change gears then. We mentioned that there's 2 topics, linearization And now the differentials. These are really weird. And we mentioned already that the major purpose for us in this class with dealing with differentials is it's an ingredient for integration in chapter 5. Specifically, this is needed in section 5.4. What's happening in 5.4 is, well, once you take a derivative, if you need to integrate something, you're unwinding that derivative. So we have to learn how to undo the power rule. We need to learn how to undo all of our differentiation formulas. And one of them that we'll be undoing in section 5.4 is the chain rule. If you want to do the chain rule in reverse, the differential is what you need, which seems really wild. There's no mention of chain rule at all in this. But the reason it's going to work the way it does is the differential is going to allow us to do a change of variables and start unwinding a chain rule as a derivative. So we start off with y equals f of x. F of x has to be differentiable. Now watch out for these words right here. The differentiable just means the derivative exists. But if you see this one, differential, you're talking about something completely different. That's almost unfortunate. The terms are matching up way too much. And we can't do too much more about it except, italicize it, bold it, blow it up. But we're talking about a differential now, so a whole new concept. The differential is indicated in this way. You take dy, that's just a symbol. This would be considered the dependent variable. So dependent variable. All of dy as one thing is considered a one symbol as a dependent variable. Here we have f prime of x and then dx. X is an independent variable. Just like we expect x to be independent unless said otherwise in this format. But there's another independent variable here. It's the dx. Dx, just like the dy, is one whole symbol in this format. So it's also another independent variable altogether. We won't be plugging in different values for dx or x to get a different dy in section 5.4, but it's good to know what we're dealing with. This is an ordinary variable. Algebraically, it plays the same as a variable would, and same with dx. Oh, I broke my arrow. We'll fix that in a moment. So at the moment, think of dy, dx in this context as being just ordinary variables. This could have been, say, a z, this could be a u or something else. But the massive confusion about all of this is if you change the context, which we're about to do right here. How do I put it in a new one? So we'll just kind of make it happen some way. There we go. If we change the context and talk about this, dy dx, this is not a differential any longer. Even though, sure, over here you could divide by dx and put it under dy. This had a context that we were talking about a differential, so that was allowed in this situation. But here, this is a derivative, and that whole thing, dy dx, represents one entire symbol representing the derivative, f prime at x. And it is one symbol. We don't think of actually literally dividing. There's no division here. We don't think of dy as being different from the dx here. We think of that one whole symbol as being the limit as h goes to 0 of f at x plus h minus f of x divided by h, where that's our definition for the derivative. But in the land of differentials, dy dx have an entirely different meaning. That's unfortunate. It is definitely a little bit confusing, but we'll talk about those matters back in 5.4 once again. Really, our whole goal here today is just practice working with differentials. Any questions, folks, before we try a few out? Okay, let's start off with on part A. Let's let y equal cosecant of t. So we want the differential of this function right here. the format goes, well, if our variable is y, we start with a dy. So that's where that goes. Next thing we have to put in is a derivative. That's matching the f prime of x from right here. So differentiate cosecant t, and we'll have the middle portion, f prime at x. Well, it's a cofunction, so guaranteed you get a negative sign. Secant and cosecant, when you differentiate them, they bring back the secant and cosecant part. But this one comes with something else. It's going to be cosecant, and what was the last of it? Good call. It's both cofunctions, cosecant, cotangent. So the derivative of y becomes negative cosecant t, cotangent t. And now I have to put in this part. It's not dx in our problem. This is where differentials get a little bit weird. Anyone see what must go right here as opposed to dx? Exactly. If the independent variable is t, we put in dt right here. I want to highlight these in yellow because we have to be very suspicious of those symbols every single time we calculate a differential. If it wasn't a y equals, if it was, say, a z equals, we would have done dz. The variable was x, we would have done dx. So the dy comes from the y here, and the dx comes from the x right there in the original definition. You know, once you get a handle of the differential, you're not doing anything super special. All we did is we differentiated this, put it here, and then we formed an equation with dy on the left, dt on the right. Somehow, some way, this is going to undo a function composition so that we can unwind a chain rule in section 5.4. Any questions or comments at all, folks, on getting through that first one? Okay, another thing I should mention, when I write this as an exam question, this is a tough exam question. Not because the computation's hard, but because of this right here. I'll often do something like this on a real exam. I'll italicize it. I don't italicize things often, so that'll be my way of saying, hey, watch out for this one. It's not your typical problem if it's asking for a differential, especially if it's italicized or even in bold to be extra emphasis. But let's try this out again for part B. Let's let this function be kind of weird. It'll be r. R might stand for radius of something. And it's going to be secant inverse of theta. So that's our function right there to get through. Before we get through this one, some of these derivatives are definitely not as familiar as the others. You definitely want to have your original trig table memorized down pat. And after your original trig tables memorized, we ought to have the table for your inverse trig functions memorized. For this one, the derivative with respect to x of secant inverse x, this one becomes a 1 over something that goes like this. And x goes into this location. And anyone recall what should be in here? Is it 1 minus x squared or is it x squared minus 1? Good call. The 1 minus x squared, that's only for sine inverse, cosine inverse. This one becomes x squared minus 1. So with that there, we now know what the derivative is going to turn into. That's the part in the middle. Let me actually just take a screenshot. That would help out. So we know the part in the middle, the f prime at x, is just going to be the derivative of that. But now we need to be really careful. When we go to form the differential, there is no dy because we started with a value of r. We'll say dr instead. Will be equal to, we place in the value of the derivative just calculated. So this right here, but we need the right variable. I wrote this out as a generic formula for x. Our variable is theta this time. So 1 over theta square root, theta squared, minus 1. And last thing we put over here, anyone spot our last portion? Good call. The variable's theta, d theta, should be the last part of that differential. So that's 2 down. And again, the trickiness about this is not as much the derivative, which is in blue. It's more about getting the symbols to the left and the symbols to the right accurate. Without accuracy on those symbols, we could easily get stuck when we're trying to do this in chapter 5. Well, we're kind of running out of questions, actually. Let's try maybe one more, and then maybe we'll take a peek at the next section and call it a day a few minutes early. Does that sound all right to folks? Okay, so here's our last problem for the day. For part C, let's maybe put part C on the next page. That seems like a good plan. Let's find the differential of x equals t times the natural log of 4 minus t. So that's our function we're dealing with. And it looks really bizarre in the setup. X, because it's on the left-hand side completely isolated, that's the dependent variable this time. It might be, say, a directed horizontal distance from a starting point after time t. T is our independent variable on this one. So first thing we need is, well, we can start off pretty quickly on this one. Let's maybe just write it all in line this time. On the left, anyone see what should be the right portion?
Yeah.
Exactly, dx for the left-hand side. Then on the right, when we go to put it in, that should be a dt. Maybe we'll put it in next, but let's calculate the derivative right here, and then we'll put in dt. This one has to use the product rule, so I'll calculate this one carefully. First, I'll take the derivative of t, which comes out as a 1. We're differentiating with respect to t. I'm going to copy in the natural log of 4 minus t. And then we'll put in a plus. This time, copy down t, then multiply by the derivative of the natural log of 4 minus t. This one's a chain rule, so let's do this one pretty carefully. It's 1 over something multiplied by the derivative of that something. And the something is the inner function, 4 minus t going inside here and right here as well. Now we know a dx also comes into the picture, but it's going to come into the format as a dt to match that right variable there. But if I write it out in this format, there's actually an algebraic mistake here, which is subtle to see. It's not about the derivative, but yeah, question first. Oh, this right here?
Yeah.
It was about going through the product rule on that one. When I went to calculate the derivative of x, it was really, sorry, just trying to see if I can sneak in some space right here, see if that works. Hey, that almost never works. Usually the ink gets a little bit messed up. Essentially what I was doing was this. When we differentiate that function here, we take the derivative of t and then copy natural log 4 minus t, then go plus, copy t, and then multiply by the derivative of the natural log 4 minus t. So this was really just through the product rule, and the whole result ended up right here. Does that make sense with the product rule on this one? Awesome. So after the product rule, let me just indicate it here. We have our derivative in blue doing the product rule in this thing. We have the right symbol dx, the right symbol dt, but there is still a mistake inside here that is absolutely hidden. Has anyone spotted it at the moment? Good call. We do still have to differentiate that, but that's not quite what the mistake is on this line. Yeah, go ahead. Exactly. When we write out like this, we're assuming f prime at x. Well, it could have multiple terms, and when it does, it absolutely has to have a bracket around it. Good call on that. That's really easy to miss, but remember, dt is a variable ordinarily like in algebra. If your derivative has multiple terms, you will always need a bracket around this portion right here. Next thing you need to do is just finalize this derivative, calculate that derivative 4 minus t. Then we'll have the full differential before my voice gives out. Any other questions so far, folks? Okay, so to finalize this one, we're going to get that dx equals bracket natural log 4 minus t. Now, there is a plus right here, and t is gonna go in the numerator, but that derivative is a -1. So overall, I'm gonna write negative. Here's t in the numerator. 4 minus t. We can close the bracket, throw in a dt. And that's the full differential finally on this one right here. So the only way it can really get tricky is put in a nasty derivative. Product rule, quotient rule, chain rules can come into play. But this is the tricky step right here. With multiple terms, sometimes you do need brackets to enclose your derivative so that dt is multiplying the whole thing. Well, any last questions, folks, on our last differential here? Okay, again, it's a weird concept. We'll review this again when we're in chapter 5. It's here because it is related to linearization, but the actual use of rule of differentiation, the actual use of differentials for us, so that's a hard word to say, won't be in linearization, it'll be for chapter 5. Well, have a great night, folks. If I didn't hand back your exam, I do have the pile here. And if you're not here in class today, you're welcome to just shoot me an email and I'll be sure to get it back to you. When we come back on next class, we'll be in the hyperbolic function section. It'll look like trigonometry with just one tiny little modification in there.
I can already tell integrals are gonna be huge, aren't they?
Sorry, what was that?
Integrals are gonna be huge. We're a line derivatives, I'm gonna assume that we're gonna get the mass of the equation and then line it.
Actually, it's not too bad. We're kind of getting over the hump as far as like lots of algebraic work. The integral equations don't get too bad in this class, but then in calculus 2, they start to. Yeah, calculus 2 has lots of stuff like that. It focuses a lot more on integration. We're focusing a lot more on differentiation.
Cool, that's fun.
It will be. Any questions, good?
More disappointment. I'd never actually failed a test this time.
Oh, yeah.